Falling into the Sun simulation, Remake, is a physics-based computer simulation designed to demonstrate the motion of an object under the gravitational influence of the Sun. The main idea of the simulation is to show what happens when a spacecraft, asteroid, or other object moves toward the Sun. As the object gets closer to the Sun, the gravitational force acting on it increases, causing its velocity to change. The remake aims to recreate the original concept while improving its graphics, physics calculations, interaction, performance, and overall user experience. Through this simulation, users can visually understand concepts that may otherwise be difficult to understand through mathematical equations alone. The project combines physics, mathematics, programming, animation, and visualization to create an interactive representation of gravitational motion. The main objective of the simulation is to demonstrate how the Sun's gravitational force affects the movement of an object in space. The simulation allows users to observe how an object's trajectory changes depending on its initial position, velocity, and direction. Another important objective is to demonstrate acceleration caused by gravity. When the object moves closer to the Sun, the gravitational force becomes stronger, causing the object to accelerate. The simulation can also demonstrate different types of trajectories, including objects falling directly into the Sun, objects moving around the Sun in an orbit, and objects passing near the Sun and eventually escaping its gravitational influence. The remake also aims to provide an interactive environment where users can change different parameters and immediately observe the effect on the object's movement. This makes the simulation useful for both educational purposes and experimentation. The simulation is based primarily on Newton's law of universal gravitation. According to this law, every object with mass attracts every other object with mass through gravitational force. The gravitational force between the Sun and the simulated object can be represented by the equation F equals G times m divided by r squared, where F represents gravitational force, G is the gravitational constant, m is the mass of the Sun, m is the mass of the simulated object, and r is the distance between the object and the center of the Sun. As the distance between the object and the Sun decreases, the gravitational force increases, because the force is inversely proportional to the square of the distance. Using Newton's second law, F equals ma, the gravitational acceleration can be calculated as a equals g times m divided by r squared. This acceleration is always directed toward the center of the Sun. These mathematical relationships form the foundation of the simulation and determine how the object's velocity and position change over time. Before the simulation begins, several initial conditions must be established. These conditions determine the starting state of the simulated object and have a major influence on its final trajectory. The initial position defines how far the object is from the Sun and where it is located relative to the Sun. The initial velocity determines how fast the object is moving and in which direction. For example, if the object has very little sideways velocity, gravity may cause it to fall directly toward the Sun. If it has an appropriate tangential velocity, its path may curve around the Sun and produce an orbital trajectory. If the object has a very high velocity, it may pass near the Sun and eventually escape its gravitational influence. Other initial parameters can include the mass and radius of the Sun, the mass and size of the simulated object, the simulation time step, and the starting simulation time. Providing adjustable initial conditions makes the remake more flexible and allows users to conduct different experiments. The simulation algorithm is responsible for calculating the object's movement continuously. At the beginning of every simulation step, the program calculates the distance between the object and the Sun. It then uses the gravitational equation to determine the magnitude of the gravitational acceleration. The direction of the acceleration is determined by the position of the object relative to the Sun, because gravity always pulls the object toward the Sun's center. After calculating acceleration, the program updates the object's velocity using the acceleration and the selected time step. The new velocity is then used to calculate the object's new position. The simulation time is also increased by the selected time step, and the entire process is repeated many times per second. This repeated process creates the appearance of continuous motion. The program can also include collision detection to determine whether the object has reached the Sun. If the object's distance from the Sun becomes smaller than the Sun's effective radius, the simulation can display a message indicating that the object has fallen into the Sun, and can then stop or restart the simulation. Visualization is an important part of the remake, because the purpose of the project is not only to perform calculations, but also to make gravitational motion easy to understand. The Sun can be displayed as a large central object, while the simulated spacecraft, asteroid, or particle can be shown as a smaller moving object. A trajectory line can be drawn behind the object so that the user can see the path it has followed. This makes it easier to identify whether the object is falling into the Sun, orbiting around it, or escaping. The interface can also display useful information such as the object's current distance from the Sun, velocity, acceleration, simulation time, and initial velocity. Controls such as start, pause, reset, speed, zoom, and velocity adjustment can make the simulation interactive. A well-designed interface allows users to change parameters and observe the results immediately, making the simulation more engaging and educational. Testing is necessary to ensure that the simulation behaves according to the expected laws of physics. Different starting conditions can be used to test the behavior of the system. In the first test, an object can be given a very small or nearly zero tangential velocity, causing it to move toward the Sun. The object's speed should generally increase as it approaches the Sun. In another test, the object can be given sideways velocity, which should cause its trajectory to curve. With suitable initial conditions, the object may enter an orbit around the Sun. A high initial velocity can also be tested to determine whether the object can escape the Sun's gravitational influence. The simulation can also be tested using different time step values. A very large time step may produce inaccurate or unstable results, while a smaller time step generally provides smoother and more accurate motion at the cost of additional computation. The results can be analyzed using trajectory diagrams and graphs showing distance, velocity, acceleration, and time. Conclusion and future improvements. In conclusion, the Falling into the Sun simulation, Remake, provides an interactive way to understand gravitational motion and orbital mechanics. The simulation demonstrates how the Sun's gravity continuously influences an object's trajectory, and how gravitational acceleration becomes stronger as the object approaches the Sun. It also shows that initial velocity and direction have a major effect on whether an object falls into the Sun, enters an orbit, or escapes. The remake can improve upon the original simulation by providing better graphics, smoother animations, more accurate numerical calculations, and interactive controls. In the future, the project could be expanded into a three-dimensional simulation containing multiple planets and other celestial bodies. More advanced numerical methods could be introduced to improve accuracy, and relativistic effects could be considered for objects traveling very close to the Sun. Additional features such as solar flares, heat effects, realistic textures, camera controls, energy measurements, and data export could also be added. Overall, the project demonstrates how programming and physics can be combined to create an educational and visually understandable model of gravitational motion.